Hello everyone, I am Bapan Gain. Me and my friends Dibbanan and Shamrat from M.Tech CSE IIT Patna are going to present about our findings on image super resolution. So we'll talk about the contents of the slides. So at first we'll talk about deep learning and image resolution, and we'll talk about an architecture called SRResNet. Then we'll show our proposed changes to the architecture, and then we'll show the results and conclude. So at first we'll talk about image resolution. So why do we need image super resolution? So in today's world we can see that we are clicking photos here and there everywhere, and in many cases we can see the photos are actually low resolution. This comes from many factors. One of them is very bad quality of cameras, like in low resolution smartphones and like CCTVs, and also satellite images like that. And another factor is in nights and in absence of good light, we can see that the image quality gets very bad. So to get good resolution images from such situations, we need to somehow enhance the image from low resolution to high resolution. So like in case the image is blurry or some details are not available, we can somehow create the high resolution image, and this will provide more details to the image. So this method has a very large number of practical applications like medical image analysis and satellite image analysis, because in this type of cases these are very crucial, but it is very difficult to obtain very high quality images from these cases. So why are we considering deep learning for solution of this problem? So as we know, deep learning networks are universal function approximators, and we can present this as a function like so. In this example, so d is the degradation function, and I of hr, this one is high resolution image input, and this one is something loss. So we are provided the high resolution image, after degradation we are getting like low resolution. So like we can reverse this, and we can somehow try to get the high resolution image. So as in the example we can see there is an image of butterfly, and here some parts of the image, and here also we can see that image is little bit blurry, and after like performing image super resolution, we can turn this low resolution image into high resolution one. So we can see this image is very much clear compared to this one. Similarly, for second example, we can see that face of the person is very blurry, because the original image is actually was very low resolution, and if we try to like kind of zoom it, then it will be very blurry. So after performing several iterations of like low to high resolution transfer, we are getting this result. So we can see if we compare this one to this one, we can see there is huge improvement, and like this one is much more detailed and much more clear. So how it can be done? So we'll talk about the architecture for this low resolution to high resolution transfer. So the full form of the SRResNet is super resolution residual network. So this was introduced by a paper, photorealistic single image super resolution using a GAN, in 2017, and this actually used ResNet architecture, which was published in 2015. So in this case, this serves as a generator for SRGAN. So what happens in SRGAN is it is actually stuck, usually gets stuck in local optima, and if we like use this method, it is like it actually avoids the issue that getting stuck in local optima. So we'll see the architecture. So here is the architecture. We can see that there are 16 residual blocks, and each of the blocks contain this sub blocks. So one is convolution layer, then batch normalization, and like that. And similarly for each block we are using 3 into 3 filters, and uh, the authors also have added these other blocks. And for like a activation function, we are using parametric ReLU. So this one is similar to a leaky ReLU, but in addition, it is like a parameter is given as a threshold. And for loss, they are using mean squared error loss. So that's all from my side. Now Dibbanan will present about our proposed changes on this architecture to improve the results. So that's all. Thank you.
Hello everyone, I am Dibbanan Bandyopadhyay. Now I am going to present how we have implemented our model. So I would like to present firstly the proposed modifications that we have done, and the main things we have done is twofold. So we have used the perceptual loss for training in place of MSE loss function. So what MSE loss functions does is that it chooses the average of all possible images in the manifold. So if we choose a set of images and if we use MSE loss function, so what it does is that it smoothens the output. So the output images are very smooth and the sharp edges of the images are not very much reflected. So for sharp images that have the pixel values ranging any values, and the subsequent pixel values might also get very low or high value in this kind of situation, MSE loss function does not give us very good output. So what we do is that we have used perceptual loss for training, and another thing we have done is that we have removed the batch-norm layer. So the paper enhanced deep residual networks for single image super resolution by B. Lim et al. Proposed that removing the batch-norm layers can sometimes enhance the output of the quality of the image. So in the right hand side in this picture we can see that the issue with MSE, and when we use MSE loss functions, the super resolution images that are output from the model are kind of smoothens out. So these kind of things can be overcome by using the perceptual loss, as we will show now. So these are the experiments regarding what we have done. So we have tried to build the architecture of SRResNet from scratch, and what we do is subsequently is that we have removed the batch-norm layers from the residual blocks, and we train the model using both the MSE loss and perceptual loss to compare them. So there are four specifications that we have explored. The first specification that we have explored uses the mean squared error loss function, and we actually use the batch-norm layer in the residual block. And in the second specification we have used the mean square error as well, and we do not use the batch-norm layer in the residual blocks. And in the third specification, in place of mean square error MSE loss function, we have used the perceptual loss, and we also use the batch-norm layer in the residual blocks. In the fourth specification, perceptual loss has been used, and we do not use the batch-norm layer in the residual blocks. So these are the four specifications, and depending on each of the specification, we will get different results. So these are being shown in the next slide. So this is the result. So we first show the result when we use the mean square loss function, and depending on whether we use the batch normalization in the residual block, yes or no, we are showing the results. We have trained the model for 50 epochs, and the PSNR, that is the metric for the super resolution. So there are two dataset in the whole set of data set. So one contains five images, so this is called the set 5 dataset, and another one contains 14 images, so this is called set 14 dataset. So we measure our model's performance for both of the dataset, and depending on batch normalization we are showing these results. So we can see that for when we do not use the batch normalization and the loss function is mean square error, for 50 epochs of training, the PSNR we get is the best for the set 5 dataset, and also for the set 14 dataset this is the best. among 24.7 and 25.9. So we can infer from that is that when we use the mean square loss function, the better thing to use, that we should not use actually the batch normalization in the residual blocks. So this is what we can infer from these results. So one of the problem in our implementation and subsequent experimentation is that we have limited resources due to having very large count of parameters. We could not use the model to actually train it until it is converged. So these are some of the limitations, and this is the second result, where we use the perceptual loss function, and depending on batch normalization we are getting different results, actually PSNR values. So in this case also we have only tried to actually train the model for larger epochs, but due to resource constraints we have to limit ourselves for 20 epochs only. And thus whether we use batch normalization or not, the results still remains the same in case of MSE as happened. So for the perceptual loss also, when we do not use the batch normalization, the PSNR value is larger among the two. So when we use it, we are getting minus 0.2, which is very low. But when we do not use the batch normalization, we are getting higher accuracy. But these are not actually the best accuracy that we can achieve from our model, as we only train it for 20 epochs. So these are some of the caveats of our experiment. So the main thing we have to constrain ourselves to is the space constraint. So we have limitation of only 15 GB of GPU RAM, and we could only use the free services offered by the Kaggle and Google Colab. So this is the space constant limitation, and the result of using this thing is that we have to limit the batch size. So the state of the art models and the models that has been explored previously by many authors, they have used 32 or 64 batch sizes, but we have to limit ourselves to maximum of 2 or 3 examples per batch. So we think that more batch size and training time might improve the reconstruction of the model. So what we can take from these results is that when we do not use the batch normalization, the results might get improved, but due to the and also we can use the perceptual loss, but as we have explored only 20 blocks of training, we could not be sure about what we have to do. But I think personally that using the perceptual loss in place of MSC might improve the performance quite a bit. This is all from my side. Thank you everyone. So my friend Samrat Mukherjee now will tell about the code and how the whole thing is being implemented. Thank you.
Myself, Samrat Mukherjee. Now, I'll be going through the code which we have used for our experimentations. First, we import all the necessary libraries that we need. Then, we define the dataset class. So, first we have the data path, then crop size and scaling factor, the amount we want to scale the image. Then we define some transformations of the input image and the target image, all of them. Now we define the get item in order to get an element based on the index value. After that, we define the model. So as you can see, we have mentioned earlier that we will be using the SRResNet, which is used as a generator network for the SR-GAN model. Now, as you can see, SR-GAN in the paper, they have used 16 residual blocks. Each of the residual blocks contains a conf layer followed by a batch norm, then PReLU, then again conf and batch norm followed by element wise sum. We have 16 blocks of residual blocks. Then we have another conf and batch norm, which has an element wise sum from the initial image before the residual blocks, and then we use pixel shuffle layers in order to upscale the image. The way pixel shuffle layers works is it reduces the number the channel by a factor of r square, while increasing the height and width of the image by factor of r. So we followed the exact architecture that the paper has mentioned. We first define a convolutional block, which will be taking p-relu, leaky relu, or tanh, but we have used p-relu only. Then we append the first conv 2D layer, then the batch norm, then another p-relu, which is according to this one. And as per the activation that is coming, we have used p-relu or leaky relu with a probability of 0.2 and or tanh. Okay, then we define the forward pass. We use the sub pixel convolutional block in order to, for the pixel shuffle layers, in order to increase. So the pixel shuffle block is the entire thing. First we have a conv, then pixel shuffle, then p-relu. That is what we define here. Then we have the residual block, which we describe. It has, like, in the first it has a conv block followed by another conv block, and we use the input, and this is how it has been computed as per the diagram. So now the SRResNet, the entire architecture comes up with first the con blocks, which indicates this one, and then 16 of the residual blocks. N block size is mentioned as 16 as per the paper. We have scaling factor of 4. Okay, and then we perform, add the pixel convolutional block as well, and then we define the forward propagation. Now for this experimentation, we have used a diff2k training data set, which is available on Kaggle. Okay. Now we use the CUDA, the GPU. We use the GPU. Although I will not be running the model in this video, but we have used it. We have run it. Currently, it is off because it's for one epoch. It takes around 6 minutes of time, so it will be very lengthy if we run the model right now. And if the model we have already existing the model, then we upload it. Otherwise, we define the model from scratch. Then we put the model in the device and in the GPU. Now, as we were mentioning that there are some issues with the MSc loss. So the paper, like the original paper titled photorealistic single image super resolution using a generative adversarial network, and they have proposed one another loss function. They have used another loss function which was proposed in another paper about perceptual loss. So we have used that in this work. So we define the perceptual loss. Now for defining the perceptual loss, we take the feature space representation of the images. That is what we are having in this part. So we for the residual blocks, there is one feature representation, and then there are 3 feature representation that we are taking into consideration. And these are the for the first till 4th, for 4th till 9th, and the last residual blocks. Then we make the param dot require grad equal to false in order to not using the gradient computation there, because we want the feature space representation only. And then we perform some rescaling and transformations, and then we uh, iterate over all the blocks that we defined here in order to compute the representation of input and the target in that layer, in that block, and then we add it in the loss function, in the loss value. That is the definition of the perceptual loss. This is the summary of the model based on the output shape that we have. Now we have experimented with both the loss functions, like the MSc loss function as well as the perceptual loss function. So if you want to toggle between either of them, we just need to comment out the other line. So now we define the train and test data set, which is actually the validation data set for this case for the training purpose. Then we'll load the data set. We define the data loaders for train and test, and we train the model. Okay. Now, to train the model, we put the images in the GPU. For each backside, we put the images in the GPU, both the high resolution and low resolution, and then we pass the low resolution image through the model to get the super resolution image, and then we perform the we compute the loss function based on the criterion that we are using. Then we clear out all the gradients, the and then perform the loss back propagation. And to save memory, we empty the cache as soon as we complete one iteration. A similar thing goes around for the test loader also, which is actually the validation in this case. And then we print the current status of the training. So this is the status that we have achieved. We have got for the perceptual loss, super resolution resnet, while training with the perceptual loss without the batch norm in the residual blocks. So we don't use this batch norm layer in this residual blocks. This is the result that we have achieved. We have described that result in the slide. Okay. Now, in this part, in this code, we perform the testing of our models using the set 5 and set 14 dataset. Now set 5 and set 14 are pretty common dataset and pretty standard dataset for this particular task. So this is where we have already uploaded those models here, and then we define the model again so that we can upload here. We define the model class. This is the path that we have. So we have uploaded the model. We load the model. We print to check if it is the correct one. And then we define the dataset data loaders for the data loader part. Then we define the data loader and then perform the test of those set 5 first. The set 5, so what we obtain is a 30.776, which generally differs if we perform like many times, but all in all it is more than 30.5 as we have seen. Now this 30.77 or 30.5 that we have mentioned, we have been very close to what the actual paper has achieved. So for the SRResNet in the set 5, the original paper using the MSE loss have achieved a PSNR of 32.05. Now we unzip the set 14 dataset and do similar stuff. We achieve around 24.7029, whereas the paper originally has achieved 28.49 PSNR while using the MSE loss in the set 14 dataset. That is using the batch norm that we have mentioned. Without the batch norm, we have achieved around 30.68 on the set 5 dataset, whereas 25.98 in the set 14 dataset. We have extensively used the ideas from different papers and different blogs that we have mentioned and that we are mentioning here in the references part. That's all from my side. Thank you very much.